yesterday we talked about slip, which is dislocation movement, and that's how plastic deformation occurs in lots of different materials. Basically, all materials is based on dislocation movement whenever you have plastic deformation. So just a reminder, plastic deformation is caused by the breaking and the reforming of bonds, and the breaking and reforming bonds is aided by dislocation movement. So it's important to have dislocations and to understand the interaction between dislocations, between a dislocation and impurities, and also dislocations and grain boundaries. And we talked about cold working as a way to change the number of dislocations, but also to change the size of grains, and therefore either increase or decrease the amount of grain boundaries. So cold working. And you could calculate the amount of cold work a material has based on the deformation that has been created. A0 is the initial cross-section area. AD is the cross-section area after cold work. So we know by increasing the deformation of a material, we can increase the number of dislocations. We can increase the amount of grain boundaries. And both of those things cause reduced dislocation movement. Reducing the dislocation movement will increase hardness and strength, but decrease ductility. Okay. So by reducing dislocation movement, you can increase strength, you can increase hardness, and you decrease ductility. But what if you want ductility? So let's say for some reason you have to work a material. So like making aluminum foil or any kind of foil, a thin sheet of something. You have to roll the material. So you feed a piece of aluminum stock into a roller. So you feed a piece of metal into a roller so that you can make a thinner sheet. Okay, that's something very, very common to make thin sheets of something, foils or any kind of material, metals, things that can be plastically deformed, obviously, okay? And so you do this, but you want your metal sheet to be ductile. You don't want it to be brittle, and you don't want high hardness in here. So what can you do? You've already cold worked it just because you have to in order to get this shape. But you don't want the increased hardness, you want to keep the ductility, so what can you do? We could do what is called annealing. It's basically taking the material to a higher temperature for different amounts of time. When you heat treat a material, metals, you have 3 stages for annealing. Stage 1 is recovery. Stage 2 is recrystallization. Stage 3 is grain growth. Okay, so for example, if we look at a piece of metal that has been rolled, so let's say we look at it under a microscope. Before the rolling, maybe it looks something like this. Okay, you have grains. And then you roll the material and you look at it under the microscope, and your grains may be elongated like this, something like that, because you're pushing everything in one direction, flattening it, so you get a different grain. And so then you take that plate and you put it under a high temperature, and recovery is at elevated temperature, and the atoms are going to, you're giving energy to the atoms inside this material, right? They have energy now. When they have energy, they're going to want to go to the lowest energy state possible, right? So for any material, it always wants to go to the lowest energy state possible. Sometimes it's stuck. It can't go to a lower energy state. But if you give it some energy, then it can move itself into a lower energy state. So you can think of it like energy. This is a high energy state, lower energy state. So your atom is here. It wants to go to a lower energy state, but there's some energy barrier. And so it can't go to this lower energy state unless you give it enough energy to overcome the energy barrier to get to the lower energy state. So it's the same thing. If you think about, I drink coffee, so I always use coffee as an example. If you have a jar of coffee beans, right? These coffee beans are not at the lowest energy state. They could go to a lower energy state if they are down here. But they're kind of stuck in the positions they are in, okay? But if you shake the jar, then the coffee beans will have extra energy and it'll find its way down to the bottom, right? And so that's the same idea as annealing. You're giving it a little bit of extra energy so that the atoms themselves can find a lower energy state to exist in. So that's what happens during recovery. You're giving the material enough energy to find a lower energy state, so you get decreased dislocations. So in cold work, we added dislocations. In recovery, we could remove a lot of the dislocations. In recrystallization, so if you continue to keep it at that higher temperature, you can actually get formation of new grains. So that takes a little longer. You can actually get grains that start to grow. So let's say here, you get a new grain that starts to grow, and maybe here another one, and here another one. You get grains that start to grow that is growing in an ideal structure. So it's not in this deformed shape. It's growing usually spherically because that's the lowest energy state for any grain with the least amount of surface area to volume. So it starts to grow new grains. That's recrystallization. And the reason it grows new grains is because the new grains are in the perfect crystal structure, and therefore it has a lower overall energy state. And then grain growth, the new grains get larger. So these grains start to grow and they get bigger. So this is after cold work. And then after grain growth, annealing, you get large grains again that are not. So even though you still have a plate, you still have a thin plate, if you look under the microscope, the grains will have been reformed in a low stress, low energy state. So a lot of times when you're working metals, you're working between cold working, increasing defects, increasing dislocations, making smaller grains, and then you're working with annealing to reduce dislocations and to grow bigger grains, reduce grain boundaries. So a lot of times you're working between those two, and oftentimes you're working repeatedly, one and then the other, one and then the other. So if you wanted to make really small and thin sheets of metal, you might roll it once. It becomes harder because you've cold worked it. And you can't roll it again because it becomes too brittle. If you try to roll it again, that hard material, it might crack. And so before you roll it again to an even thinner sheet, you need to anneal it to regrow the grains. Then you could roll it again into a thinner sheet, then you anneal it again, and then roll it again into ever thinner sheets. Any questions about cold working and annealing? So I put an article on E3 for you, another article, and this time it's about something called master bladesmith. So I encourage you to read it. It's not required, but for me it was a fun article to read. And it is about an organization that certifies people who work on blades, so swords, knives, things like that. Of course, swords and knives are all made out of materials, and it's really important for swords and knives to be strong, right? The edge has to be really sharp and hard. So it has to be hard because it needs to be able to cut through things without bending, right? But at the same time, the sword has to be really flexible so it doesn't snap in half, right? If you're cutting something, the sword's going to bend. And if the sword is brittle, then it'll crack or snap in half. So it's really difficult to make a really good knife or a really good sword that both has really high hardness, but also high ductility. And that article talks a little bit about it. And a little over 200 people who are certified in the world as master bladesmiths as of today. And in order to become a master bladesmith, you need to do 4 things. Well, 5 things. Okay, so you need to make 3 knives or blades. And 2 of them has to be beautiful and perfect in terms of the heaviness, the look. It just has to look really, really pretty. Okay? So those are for demonstration, just for looks. And then you need to produce 1 blade. It's, I think it's like a 6-inch blade. It's a curved Bowie knife shape. So you have to make 1 that you will actually do a test with. Okay? So the test to become a master bladesmith is that you have to, this knife, with that 1 single knife, you have to be able to do 4 things. 1, you have to be able to cut through a 2.5 centimeter thick rope. Maybe like this, 2.5 centimeter thick. Maybe a little smaller, like this. You have to, a very strong, tough rope. You have to be able to cut through that rope in 1 swipe. Okay, so that's the first test. The second test is that you have to be able to chop through a piece of wood that's 0.6 meters thick and 1.2 meters wide. So with that same knife, you have to be able to chop through a piece of wood that's that thick and wide, okay? And you have to do it twice. So you chop it through once, and then you chop through it again with that same knife. After you've chopped through that piece of wood, you take that knife, and you put it against your skin, and you have to be able to cut hair. In 1 swipe, it has to be able to cut hair off of your arm. So it has to be that sharp in order to cut hair, okay? And then, if it can do all of that, then you put your knife, and you have to be able to bend it 90 degrees without the knife breaking. Okay, so it has to be able to bend. So that's what it takes. You have to make a knife that can do all of those things. And if you can do that, then you become, and then they inspect the other knives that you make, and it has to be beautiful and perfect. And if you pass all of those things, then you become a master bladesmith. And the article is about someone who is a master bladesmith. He used to be a chef, and he worked in restaurants, and he was always interested in why some knives the chefs use are better than others. And he didn't really understand, like all the chefs that he talked to had really no idea why certain knives are better. They just know that this is my knife and I like to use it. But he couldn't really tell why. The chefs couldn't really tell him why they liked the different knives. And so he decided to look into knives. And then he started working on knives, started trying to make his own, and eventually he quit his job as a chef and became a bladesmith. So now he makes knives for chefs. And you can go on his website. His name is Bob Kramer. He's one of very few bladesmiths that actually make knives for cooking. Most of the other bladesmiths make knives for hunting or make swords. Okay. And so he makes knives for cooking. So you could go on his website to try to buy a knife. He only sells 1 knife right now that he makes. You could go online, and then he has an auction. People who have his knives and who don't want it anymore can put the knives on auction through his website, and you could bid on those knives to try to buy those. But if you want to buy 1 knife right now, you could buy it for $65,000 US, a single knife. So if any of you buy a knife from Bob Kramer, let me know. I would love to come to your house and try it out. Very interested in what it feels like to use a $65,000 knife. But what makes this knife so expensive? I can talk a little bit about knives. So for kitchen knives, most of the time they measure hardness with Rockwell hardness measurement. And we had talked about Rockwell before. The Rockwell hardness test has a range between 0 and 70. If you have a Western kitchen knife, it has usually a roughness between 55 to 60. And if you have a Japanese knife, it usually has a hardness around 65. The Western knife is what you could get in the US or in Europe, and it's soft because it's what is considered an all-utility knife. You use it to cut lots of things. It needs to be soft so that when you cut things that are like a bone, right? If you want to chop through a bone or work on a chicken, so that I have a question for Asians, especially Taiwanese and Chinese people who eat chicken. How come you don't cut the chicken according to where the bones connect? I don't know if you know what I'm talking about. You always cut the chicken just whatever. And you end up with chicken that has a tiny, tiny piece of bone inside, and so it stabs you in the mouth when you eat it. Does that ever happen to you? Like, I don't understand why you don't cut it according to where the bone ends. And then it makes sense to eat the chicken that way because you know where the bones are. Anyway, when you cut chicken bones like the Taiwanese do, you just hack away, you usually want something that's a Western kitchen knife. Because when the knife dulls, because it's soft, the edge of the knife, the edge here, will bend instead of break. It's because it's soft. So it bends. And so in order to sharpen the knife again, you just have to make the ends straight again. So a lot of times people do like rub the knife against like another metal thing. And it's not to sharpen the knife. It's not to get rid of any of the material on the knife. It's just to bend so you have a knife that's bent like that on the tip. And by rubbing it against surfaces, you're just making that tip straight again. So that's a Western knife. It's soft, it bends when it's dull, and then to sharpen it, you just make the edge straight again. So that's good for most chefs because that makes it very easy to sharpen. But it also dulls very quickly. Oftentimes, you will have to sharpen the knife before each time you use it, because it could dull very quickly after each use. Okay? A Japanese knife will have a very, very hard edge. So it doesn't bend, and it will stay sharp for a long time. But if you misuse it, so if you use it to try to chop chicken, like Taiwanese chefs do, then the knife, instead of bending like this, will actually chip. So it will the edge will become jagged and not flat. And you can rub it against, those steel things as much as you want and it will not sharpen. What you'll have to do is re-grind it. You actually have to take it to a grindstone and grind down the edge until it's sharp again. Okay, so it's very difficult, or much more difficult, to sharpen. You can't do that at home. Most people don't have a grindstone at home. You have to take it to a professional knife sharpener in order to sharpen a Japanese knife. And so that's the difference between a sort of common Western kitchen knife and a Japanese kitchen knife. And what Bob Kramer did was he wanted to make a knife that was sharp, but also that so hard and flexible at the same time. Okay. So he looked around and he saw that there's something called Damascus steel. Has anyone heard of that, Damascus? I'll write it down. It's found in history. It's legendary. People talk about how the Persians would have superior swords made out of Damascus steel, and they would not only be able to slice through their enemies, but slices through the enemy's swords. That's how sharp and how flexible these swords are. Okay. And they have a distinct pattern. You can tell that it's a Damascus sword because it has these like wavy pattern. And I'll show you a video of something you can see these patterns. But it has a wavy pattern. And it's very, very pretty. It's not something that's painted on. It's just part of the steel has that wavy pattern to it. And the exact technique has been lost. People don't know how people made it. So the way people make it now, they've tried all different ways of reproducing. And the way Bob Kramer makes Damascus steel is he takes 2 or more different kinds of steels, and he puts them next to each other. And then he puts that into a furnace, and then he cold works it so that these 2 steels are pounded together. And then he folds it over, puts it in the furnace again, takes it out, pounds it, so that it's making lots and lots and lots of layers, right? You take 2. So if you know how to make a croissant, it's the same idea between flour and butter is you're folding the flour and butter over and over and flattening it to make tiny, tiny layers. So same thing with the Damascus steel. You're folding it over, flattening it by, not with a rolling pin, but with a hammer, putting it back in the furnace, pounding it again, folding it over. And knife that Bob Kramer makes will have something between, I think he said 80 to 400 layers. And that's what makes this beautiful pattern on Damascus steel. But why does that matter? Why would that pattern make it so that it is so strong, hard, but flexible at the same time? So what they're doing by making these thin patterns is that they're actually combining 2 different materials. One has high hardness, and one has high ductility. Okay, so it's actually making 2 materials that have different properties into one. So that the material with a high hardness will give the edge, keep the edge sharp, but the material with a high ductility will keep the sword from breaking when it's flexed, when it bends. Okay, so that's the Damascus steel. And that's done by repeated cold working and annealing, cold working, annealing, so on and so forth. And then, so this is by taking 2 materials together, and then he found out there was something even better than Damascus steel with a very similar pattern, and that's called wootz. And wootz, it's another legendary Persian steel that no one has been able to replicate basically for hundreds of years. So at some point, people made wootz steel swords, and then the technique was lost. And no one has been able to reproduce wootz steel until, I think, in the 1990s by a person, and you'll see a short video of him, by a person who lives in the South, in Texas, I think, in the US. He is what is called a farrier. A farrier is somebody who makes shoes for horses. So he works with steel a lot because he makes the horseshoes. And he read about wootz one day for some reason, and he thought, let me try. I work with steel. I have a furnace. I have the raw materials. Let me try to see if I can make this. And he did his experiments over and over. He just kept trying different things, and eventually he did make wootz steel. And wootz is different because instead of putting different layers together, you start with just one. You do end up folding it and cold working it, annealing it to get the layers, but it only comes from one material. And that one material is just steel. It has a high carbon content. And by having the high carbon content, he could grow phases in it. That's Fe3C. It's called a carbide. Iron carbon is a carbide. Okay? Fe3C can grow out of the steel. And Fe3C is really, really hard. It's almost like diamond. Okay, it's very, very hard. And by working the metal just right, he could get the Fe3C to kind of line up on the edge of a blade. And that's what gives it that such a high cutting, strong, hard edge, while the rest of the steel is still very flexible. So it makes a high ductility, high hardness steel. So I'll show you the video. So that's the guy, Al Pendre. He's the American that discovered how to make it. And he has since passed away, so he's no longer alive. So that's a wootz steel. So by growing these carbides, what they found out was you needed 0.005% of vanadium. So very, very, very small amount of vanadium. Somehow the vanadium stabilized the carbide structure so that it could form these teeth along the edge. And the scientific community still don't know exactly why. It's such a small amount that they don't know why having that small amount of vanadium stabilizes that structure. But it does. And what they think happened, the reason why the technique was lost, is that no one knew why wootz was able to be made, right? No one had that understanding that you needed this amount of carbon with this amount of vanadium. They were lucky, some people were lucky because in the place in India where they were getting this iron from, it just naturally had the vanadium. It was part of the ore, part of the ground that they were getting this steel. So for certain families in Persia, they were getting this iron from India, and they were able to make this very, very strong sword, the wootz steel. But no one knew why. They just know if we get it from this people and we make it this way, we can make the best swords. And of course, this is a secret because they wanted to keep it within the family. They don't want anybody else to be able to make the same sword. So they never told anyone where they were getting this steel, this ore from. So either that family died, stopped making swords, and the connection with the supplier was gone, or maybe the supplier ran out of ore. They used up all the ore in that area, and they think, well, we move over a little bit, get more ore from this essentially the same and ship it. It should be exactly the same, but maybe the ore next door didn't have the same amount of vanadium. And so they were doing everything the same. The bladesmith in Persia were doing everything the same, heat treating it the same way, processing the metals the same way, but they could never, if the ore didn't have any vanadium, then they couldn't reproduce the wootz steel. And so the process for making the steel was lost after a certain amount of time. And so it's pretty amazing that it was rediscovered. And the main thing to remember is that is essentially these blades are really, really good because it's essentially is what is called a composite. So composite is two different materials mixed together. And it usually has what is called a matrix. It's usually a matrix and something else that's embedded inside. And so for the Damascus steel and for wootz, you have a ductile matrix with a hard additive, something that's added in to give it the hardness. And so that's the distinct characteristic of these Damascus and wootz steels. And this is also, a composite is also the same thing that we talked about when we were talking about thermal formable ceramics, right? The boron nitride and boron oxide that can be formed, shaped under pressure. That's also a composite. Now I want to move on to the next topic, and that's failure. Okay, so when things fail, they break, basically. So failure is caused by crack propagation. So when a crack grows all the way through a material, the material breaks, and that's failure. And it doesn't matter in what kind of material, all material failure are caused by crack propagation. So you have two different kinds of materials we have ductile material and brittle materials. But both are caused by crack. The failure of both types of material are caused by crack propagation. Okay, so in a ductile material, you put the material under stress, you're pulling it on the material, and this material has cracks, because all materials have surface cracks. That's just, and nothing is perfect, right? So everything has small imperfections on the surface, and you continue to pull that, the cracks will grow. So the cracks are getting bigger, the material is elongating because we have a ductile material, so there is plastic deformation. And within the material, you're going to get little voids, or little cracks, holes that happen because you're deforming the material. So there'll be holes inside the material. And then eventually, those holes will grow because you're continuing to deform. Those holes will grow, the material gets thinner from the cracks along the edge, and then eventually it will break in this kind of pattern. Okay, so it kind of has like a, what is called a cup and cone pattern or a fibrous pattern. So the surface, the break surface is not clean. So that's what happens in a ductile material. You have cracks on the surface that grow in, and then cracks inside. These little pockets are like cracks inside the material that grow out, and eventually the cracks from the outside and the cracks from the inside meet, and the material breaks. If we look at a brittle material, same, we have small surface defects, something like that. Pull on the material. This is a brittle material, so no plastic deformation, so it just cracks. From maybe this crack growing in and this crack, they meet and it breaks, and that's it. So cracks are important to understand how they affect the fracture of materials, because whenever you have fracture or failure of a material, especially if you're not expecting it, that's a problem, right? Anytime you use a material, failure or fracture is a really, really serious issue. So you need to be able to understand how cracks play a role and to be able to predict whether a material will fail or not. So there's actually some equations involved. So cracks are what are called stress risers. So I have a highly magnified view of a crack. No, inside a material, if I'm pulling on this material, stress is force divided by area, right? The stress this material experiences is the force I am pulling on it with divided by the cross-sectional area. So that's the stress experienced by the material. What happens at a crack is that at this tip, there are only very few bonds that's resisting that force. So it's essentially like reducing the surface area. So if the surface area goes down, even though the force is still the same, the stress experienced by the material is much, much higher. Okay, so that's what a crack is, a stress riser. It increases or magnifies the stress experienced by the material. So here's some equations to calculate the stress when there are cracks around. So sigma m is a resultant stress. This is a stress that's being felt by the material, or the magnified stress. This is the stress if there is no crack, so applied. A is the length of the crack. Rho sub t is the radius of curvature. Radius of curvature can be thought of at the tip of the crack. If you can insert a perfect circle into that tip, so it will look something like, right? That's a perfect circle that fits within the tip. The radius of that circle is rho. So if I have a sharp crack versus a blunt crack, so sharp, I'll have a very small radius of curvature, whereas this will be a larger. So if a blunt crack will have a larger radius of curvature. So the magnified stress depends on two things. How long is the crack, the A, and how sharp is the crack. Because the sharper the crack, the fewer atoms are involved in resisting the stress, right? And so the higher the resultant or magnified stress becomes. We also have something KT. It's called the stress concentration factor. So if you have a sharp crack, that means you have a big or small rho, radius of curvature. In a sharp crack, you'll have a small or large rho. Small? Okay. So your stress concentration factor will be, okay. If you have a long crack, that means your A goes up, and same thing, K sub T goes up, and magnified stress goes up. I brought some pictures to show you. I don't know if it'll work. Let me try it. So we know there are two different ways materials fracture. They could fracture by ductile fracture, or they could fracture by brittle fracture, right? So usually ductile materials, we expect ductile fracture. Brittle materials, we expect brittle fracture. Make sense? And in general, if we're using a ductile material, we expect ductile fracture, which is good because it gives us a warning, right? Ductile fracture, the materials start to deform. You start to see this kind of stretching, and you know, okay, time to do something about this material. It's obviously going to fail soon. Brittle fracture, you don't have that much warning. It's there, and then it's broken. Okay? And so sometimes ductile materials will experience brittle fracture, and that's a big, big problem. And that's something that needs to be understood. Why would a ductile material experience brittle fracture? And here are some examples of what happened. So this was a ship being built in the US, and while it was being built, the body of the ship cracked in half. So it's a brittle fracture. There was no warning, it just cracked in half. This is a case where the fuselage of the airplane came off. Okay? And so there was no warning, it was a brittle fracture. The plane had been flying just fine, and then all of a sudden it disintegrated. Another problem that sees brittle fracture in a ductile material very often is in turbine blades. So jet turbines used in a lot of industrial applications and on airplanes and things like that, propellers. The blades are operated at high temperature and high speed, so a lot of stress, centrifugal stress. And that can also cause a ductile material to fail in a brittle manner. So that's another example of brittle fracturing a ductile material. And this last one happened, I think in the 2000s. It's a train, a high-speed train that derailed. Obviously, a lot of people were injured, and I believe quite a few also passed away. But what happened was a brittle fracture inside the wheel of one of the, inside the train, and it caused part of the train to derail and created the disaster. So examples of materials that should have failed in a ductile fashion that failed in a brittle way, and those create large disasters. And so we need to understand why would that happen. Okay, we understand why materials break under ductile conditions, and we understand why materials break under brittle conditions. But why would a material that's supposed to be ductile break in a brittle manner? Okay. So first we need to understand a little bit about what is happening in a ductile failure. So when we have ductile failure, we also have cracks. So this is a ductile material. And you also have a crack which has a length, A, and a radius of curvature, the rho. And you might have a very sharp crack, something like this. And so we know that this is going to have a really high magnified stress at that tip. But because this is a ductile material, it's going to plastically deform at the tip. So it's going to start to look like this. It will plastically deform. So now it has a larger curvature and is experiencing less magnified stress. And eventually it might even start to look something like this, right? So because the material can plastically deform, it's ductile, there's dislocation movement, slip, and that slip is allowing the material to adjust for the crack. And inside a ductile material, you may have pockets like this. And inside that, we treat this as two surface cracks meeting together. So this is 2A. The length of an internal crack is 2A. And this radius of curvature is same based on how sharp the crack is. Okay, so you will use regardless of whether you have a surface crack or an internal void or internal crack, you will use the same equations for magnified stress. All right, so fracture toughness is a resistance to brittle fracture in the presence of a crack. So all materials have cracks on the surface. It's not possible to avoid cracks. So what happens when you have a crack and how likely will the material fracture in a brittle manner is represented by K sub C, and K sub C is defined by this equation. So Y is a dimensionless factor. It's calculated for different kind of cracks. E is Young's modulus, or sometimes also called modulus of elasticity. This is something we studied before with stress and strain, same E. And then this is surface energy. Surface energy has to do with how strong the bonds are between atoms on the surface of a material. So obviously, the stronger the bonds on the surface, the harder it is to break the bonds, the higher the fracture toughness. Young's modulus has to do with stretching the bonds, right? Stress and strain related to Young's modulus, so it has to do in the elastic region. So Young's modulus tells you how difficult it is to stretch the bonds. Surface energy tells you how much energy it takes to break the bonds. And then it depends on the crack shape. Oh, and then sigma C is the critical stress, the stress needed for crack growth. So fracture toughness is how much energy or stress it takes for a crack to start growing. It's related to the length of the crack, other parameters, geometry of that crack, whether it's a surface crack, internal crack, how sharp it is. And it's also related to how easy it is to stretch the bonds and how easy it is to break the bonds. So that's fracture toughness. So cracks are important. So if we want to strengthen a material, increase the fracture toughness, if we want higher fracture toughness, we have two options. We could either get rid of cracks. Okay, so let's talk about that first. So we can reduce the number of cracks and the length of cracks. And this is actually something that's done with glass a lot. So if you have a piece of glass, it might have, obviously, it's not going to look quite this rough. Actually, on the surface, the cracks are very, very small. And if you were to put this piece of glass on a 3-point bending test, so that's this glass rod. So you have a glass rod, and you try to bend it. Okay? And you can imagine if there's a little crack here, it's going to break really quickly, right? Okay. So in order to strengthen this rod of glass from breaking so easily, what you can do is you can get rid of the surface, because a lot of these cracks are on the surface. Cracks happen because just imperfections in the structure, but also from handling. If you're touching the surface, you drop the rod of glass on a table, little pieces of it might fall off, right? So there's just going to be a lot of surface cracks. Way more surface cracks than there are going to be internal cracks. Okay. So if you can get rid of a small amount of the surface, now you have fewer cracks and shorter cracks. Right? So that is going to, this is called chemical etching. It removes the surface layer. And so remove the surface layer, and you can actually get glass rods with a really, really high bending strength. I don't know if you do that experiment at NYCU. At Cal Poly Pomona, where I teach, normally we have an experiment like that. We give students lots of glass rods and have you put it under a 3-point bending test. Some are etched, others are not. Some are etched longer, or others are etched shorter. And you'll see that the strength, that bending strength, can increase quite dramatically, 20 times the strength. And sometimes you can actually see the glass rod bend is so strong that a piece of glass, like a slightly thicker than a pencil, okay, that glass rod will actually bend, visibly bend until it almost touches the bottom of the machine before it breaks. Okay, because we don't usually imagine that glass can bend without breaking, right? But glass actually has really strong bonds. It's a covalent bonds, SiO2, but silicon and oxygen bonds. It's a mostly covalent bond. It's really, really strong and can stretch quite a bit before it breaks. And so that's what happens when you look at glass fibers. You know, optical fiber technology, you have glass fibers. These fibers have to be able to bend around corners, right? And they're very flexible. And the reason why they can be so flexible without breaking is because they're made with very, very few cracks. And then they protect the surface. They put a layer of polymer over the surface of the glass so that new cracks don't form while it's being used. And that's why glass fibers can be so flexible, even though it's glass. And we usually think of it as being very brittle. Okay. So by removing the surface layer, you're removing cracks. So if you could remove cracks, or if you could make the cracks smaller, then you can greatly increase the fracture toughness of even brittle materials. And then the second way you can increase fracture toughness is by preventing crack growth or reducing. So like I said before, you can never remove all of the cracks on a surface. There will always be some. So what do you do if you want the material to still be strong? So this is an example in tempered glass. Okay, so in tempered glass, we know tempered glass is usually used on windshields for cars because we want that windshield to be very, very strong and not to break easily when, when you're driving. And so what happens if you have a piece of glass and you heat treat it so that it's at an elevated temperature. And then what you do is that you drop the temperature on the outside. So the temperature, the glass is under a high temperature, and then you cool the outer layer quickly. What will happen is you cool the outer layer and the glass structure is kind of frozen in place. So the glass structure is kind of frozen into whatever shape it was at that elevated temperature. but you allow the inside to cool slowly. When things cool slowly, it tends to contract, right? It'll shrink a little bit because when it's hot, it takes up more space. You allow it to cool slowly, it's going to find a shape that's going to allow it to take up less space. So the inside is going to try to shrink while the outside is locked in. So the inside is pulling the outer layer in. And the outer layer is pulling the inside out, right? So they're what I call internal stresses. So there are stresses between the outer layer and inner part of the glass. This pulling the outer layer in is going to cause the cracks to close or prevent the cracks from opening. Okay? So you're putting in stresses within the material that will make it more difficult for the cracks to open up. And so that's how you make tempered glass. You cool the outside of the material, you allow the inside to cool more slowly so it becomes more dense. So it's going to put a compressive stress on the surface of the glass, which will prevent the cracks from growing. And so achieve a higher fracture toughness. The two ways that we can increase fracture toughness, reduce the number of cracks, reduce the length of the cracks, but also make it more difficult for the cracks to open up. I think I'll stop here. And then next week, we'll talk about how do we, what happens when you have that ductile material that breaks in a brittle manner, like the pictures I showed you. We'll talk about why that happens and how do we deal with that.